Hello and welcome to our 6th video in our Advanced Trigonometry series. I am Mr. Chowdhury and today we're going to be looking at the sine rule. What I suggest before you do this video is that you've watched the videos on trigonometry before you moved on to this one. So that includes finding values of trig, Pythagoras recap, and then also exact values. So your first task in this lesson is going to be to draw a scalene triangle. You can do that in a book or on some paper. And then I'd like you to measure the angles and the sides of that triangle that you've drawn. And I'd also like you to look at where the biggest angle is, where the longest side is. That's what I need you to do. So this is where you'd pause the video and have a go at doing that. Okay, so here is a triangle that I've drawn. As you can see, I've got my 3 angles and my 3 sides. My 3 angles being 75 degrees, 65 degrees, and 40 degrees. My sides being 13.3 centimeters, 12.5 centimeters, and 8.9 centimeters. So what I would like you to have noticed is the positioning of the biggest angle with regards to the longest side. And we can see that they are directly opposite. And if you look at the smallest angle and the shortest side, they are directly opposite. And so on for the last side that we haven't looked at. And we can say that the biggest angle is opposite the longest side. And that's because of the geometry of triangles. If you think about a right angle triangle, the biggest angle in a right angle triangle is that 90 degree. The right angle is the biggest angle. And directly opposite that right angle is the hypotenuse, the longest side. This is just a geometric effect of drawing a triangle. The angles and the sides will pair up in a sense. They match up to each other. So the longest side will always be opposite the biggest angle. And the smallest side will always be opposite the smallest angle. And that brings us on to the sine rule. And what we can say is that if we were to take a ratio value of the sides compared to their angles, their corresponding angles, we can see that their values would be exactly the same. So if I had side A over sine of angle A, that would be equal to side B over sine of angle B. And similarly, both of those would have the same value as side C over sine of angle C. And this is the sine rule that you might see. You might even see it this way round, where we have the angle as the numerator. So we have sine of angle A divided by side A, sine of angle B divided by side B, and sine of angle C divided by side C. And those 3 values would be exactly the same. And we can check this with the triangle we did earlier. So I've color coded this so you can see the largest angle and the longest side are both blue, the smallest angle and the smallest side are green, and the medium ones are red. So here I've written the sine rule, color coded it so you can see where the values are going to go. I've popped the values in and I've got the answer, and I can see that to 1 decimal place they are exactly the same. Now if you were to increase the degree of accuracy, there may be a little bit of discrepancy, but that's because of the inaccuracy of measurements. When I measured this shape, when I measured this triangle, I could only measure to 1 millimeter. And I could only measure to 1 degree. If I was able to be exactly accurate, then they would be exactly the same. If I was to be perfectly accurate, if I had a computer brain where I could just measure everything exactly perfectly right, we would end up with the exact answers. To 1 decimal place, we end up with the same answer when we have the sine rule in this format, where the side is the numerator. If you had the sine rule where the angle is the numerator, where the sine of the angle is the numerator, we can see that once again, we get the exact same value. So it's really interesting to see that this is how the sine rule works. And we can use this sine rule to work out missing angles and missing lengths of non-right angle triangles. This is one way of doing it. All we need are pairs of sides and angles. Now, this may not be very convincing to some of you. So what I have done is I've made a separate video on the algebraic proof of the sine rule. And you can go and watch that in your own time. If you are happy with my explanation and you think I don't need any more proof, I believe you, then we can carry on and see how we can apply the sine rule to work out some answers. We can look at why we are doing each individual step. So let's start off with the first step in both questions. On the left hand side, we've got the sine rule where the side is the numerator. And on the right hand side, we've got the sine rule where the angle is the numerator. But we've written down the sine rule for both questions. The next step, we've substituted in our values, which is exactly the same. Step 3, from what we can see, is we've rearranged to try and make the unknown the subject. So on the left hand side, we've multiplied both sides of the equation by sine 76 to make x the subject of the equation, and on the right hand side we've multiplied both sides by 7.35 to make sine of theta the subject of the equation. Now on the left hand side we've just done a bit of rounding and got our answer. On the right hand side, however, we've had to do a couple more steps. We can see that once we plug in sine 76 divided by 8 multiplied by 7.35, we end up with this decimal. Now that's sine of the theta, but we want to work out what the value of theta is. So we need to know and remember to do the inverse of sine to find the value of the angle. And then after that, we've done some rounding to get that. So that's what the key differences and key similarities are. What we can notice is this one thing. When we were looking for a missing side, we had the side as the numerator of the sine rule. When we were looking for a missing angle, we had the angle as the numerator for the sine rule. Now you may be asking, so why do we need to do that? Well, that's a fantastic question, and we're going to look at that now. So here is a question, and we're just going to work through this. So you might want to write some steps down, but we're just going to work through this, and we're going to talk about what happens when we use different forms of the sine rule. So the first thing we're going to do is label our angles. Once we've labeled our angles, we can then figure out where the opposite of that angle is so that we can start labeling that side. So I know here's A, opposite A is this BC, so I've labeled that as lowercase a. Here's C, opposite that is 9, so I label that as C. Because we're not given AC, we don't need to consider that this would be called B. We're not going to use that side anyway, so we don't really care about it for now. So now let's try and work out what the answer is. So I've written down the sine rule where I've written the side as the numerator. I've written the sine rule down where the side is the numerator. Then I've plugged in my values. And I've rearranged it to make x the subject. And then I got an answer of 12.7 to 1 decimal place. Now let's see what happens if I used the other form of the sine rule. Let's see what happens if I use the other form of the sine rule. So once again, I substitute my values in. I start rearranging to try and make the x the subject. So I've tried to rearrange. I've multiplied by x to get rid of the fraction on the right hand side of this equation. And then I've had to divide by sine 45 over 9 to get x to be the subject. And then I get the exact same answer. Now you might be asking, well, if you get the same answer, why does it matter, sir? Well, it's a question of efficiency. Over here, I've only had to do 1, 2, 3 steps of maths. Whereas over here, I've had to do 1, 2, 3, 4 steps of maths. And it may be that you may forget to do some of these steps. And we want to try and be as efficient as possible. We're trying to save as much effort. We're trying to keep our cognitive load, the amount of things we're thinking about, to a minimum. So if we start with the appropriate form of the sine rule, it's not correct, it's not necessarily going to be the correct way of doing it. You could use either. But this one, where we're looking for a missing side, is significantly more appropriate than using the version where the angle is the numerator, because it means we have less steps to do. It just means that we can be more efficient and we can be more effective with where we are using our brain power and where we are applying these sine rules. The truth is, it doesn't matter which version of the sine rule we use. We saw earlier that regardless of the version of the sine rule, we still get the same answer. It's just about being efficient. So hopefully that gives you a very basic understanding of the sine rule. What I suggest you do now is go and attempt some questions from Mr. Amerson, or if you're feeling super confident and you want to try some things on your own, you can go on Corbett Maths and Dr. Frost and practice some questions on there. Hopefully, as I say, this has been helpful. If there are any issues, you can always come back and watch this video again. That's the power of having these videos. Go forth and be productive, and I'll see you in the next video.